solving acid and base problems. So now we are completely transitioning into not talking about general equilibrium, but specifically talking about equilibriums that involve acids or bases, right? So we are going to, in this, we're going to specify what type of equilibrium constant we have by adding the subscript, right? Before we were talking about capital K, EQ is just a general equilibrium expression or equilibrium constant. Kp was that equilibrium expression in terms of pressure. Kc was it in terms of concentration. Now, when we talk about acids, we're going to talk about Kas, right? It's an equilibrium expression or equilibrium reaction specifically for an acid, and then Kb would be an equilibrium specifically for a base. The process that we're going to use to solve these problems is the same. Right, we're still going to do an ice table. We're still going to do the algebra that's involved in that, and there's still going to be a constant that we solve for. We're just going to be specific of whether it's an acid or a base. You'll hear me a lot just call it K because that's what it is, right? All right, so let's look then at the challenge problem for today. So if we have a challenge problem where we have 0.148 molar solution of a monoprotic acid that has a percent ionization of 1.5%, we need to determine the acid ionization constant, this Ka, for this acid. Right. So let's start with talking about defining some of these terms, right? What is we talk about a monoprotic acid, right? That is going to be an acid, start purple today, where it has a single hydrogen that we can lose, right? And we don't know what acid it is, so I'm going to just call it HA, right? Where A is the anion for that acid, it's going to be an unknown, right? That is going to be an aqueous, right? Because we're talking about a Ka, this is going to be a weak acid, right? So when we put it in water, we are going to get an equilibrium, and in this equilibrium, we are going to, it's going to act as an acid, so we're going to donate its proton in the Bronsted-Lowry equation to give us this equilibrium. Right? Okay. So that's the equilibrium we're talking about. I'm going to scoot down here a little bit, and let's define what this Ka is. Right. The Ka for this reaction, again, just like all the other equilibrium expressions, is going to be the products over the reactants, right? So we are going to take the concentration of the products, H3O plus, raised to its coefficient, which is a 1, times the other product, again, 1. And we're going to divide that by the reactants, right? Where we are going to ignore the water because it's a liquid, so it's not involved in the equation or the solution, right? It's the solvent, so we're going to set it equal to 1. So this is the expression that we are going to have, right? The other thing that they defined here was this percent ionization, right? So let's take a second and look at what percent ionization is. What is percent ionization? Well, it's the amount of that species that becomes ionized, right? So in this case, that is going to be the amount that is ionized, right? The amount of the part of it that is an ion, this A, divided by the amount that's totally there, which would be this HI initial, right? Times 100 to make it a percent. Okay, so now we've defined all these terms. Right? This is in terms, this here is in terms of the equilibrium, right? From this, we don't have the equilibrium, we have some initial concentration. So if we have an initial concentration in our equilibrium and we want to know information at equilibrium, we get to solve an ice table, So where our initial concentration is the 0.148, we're going to ignore the water because it's not there. What's the initial concentration of the H3O plus and the A minus? What's our initial concentration of these two? Anybody? The moment that this hits the solution, we're going to have none of it have been ions, so that one's going to be 0, right? But the ionization, autoionization of water says that initially we're going to have 10 to the minus 7th of this. So where does equilibrium lie? Well, if we look at Q, we put these values in here into the K expression, we see that we get a number that is essentially 0 because this one is 0. Right? This is 0. So 0 divided by a number is 0. So that means that the equilibrium has to lie in this direction, which means that we are going to lose some amount of this and gain some amount of each of these. So that at equilibrium, we're going to get 0.148 minus x, 10 to the minus 7th plus x, and plus x. Now, if we look at this one, when we do this, right, this is going to be fairly complicated math, but what do we know about this value in comparison to that value? Is 10 to the minus 7 a large number or a small number? 10 to the minus 7 is a very small number, right? So even if this is any proportion of this amount gets shifted over here, x should be large. So we can make an assumption and assume that x is going to be much greater than 10 to the minus 7th, right? Which means that when we add 1.10 to the minus 7th to x, it's going to be essentially x. So this is approximately equal to x then, right? So in our K expression, Ka, this would be essentially x times x divided by 0.148 minus x, right? Everybody with me there? So now we have, in this equation, we have two unknowns, right? So we need, in order to solve that, we have to come up with another. We have to either find x another way or Ka another way. Well, the question's asking for Ka. That means we have to have another way to find x. Well, if we go over here, the percent ionization, right? If we look at this, right? Do we know the amount of A minus at equilibrium? Not the number, but we know how to represent it, right? That's going to be this x value. So this 1.55, which was the percent ionization, percent is got to be equal to x over our initial concentration, 1.48, times 100. So because we have this, we can then solve for x. And when we do that, we get 2.294 times 10 to the minus 3. Does that make sense? And when we come back up here, if we compare that x value, the 2.9 or 294 times 10 to the minus 3, that is, in fact, much, much greater than 10 to the minus 7th, right? So this assumption is true, right? And we can check it by taking the 2.294 times 10 to the minus 7, or sorry, 3, and divide it, or take 1 times 10 to the minus 7th and make that a percent. Let me do that math real quick. And we find that this number is approximately 4.3 times 10 to the negative 3%. So this or this number is less than 0.01% of that number, right? Which means that this value is going to be, when we add them together, is going to be an insignificant contribution, right? The number is still going to round to the 2.294 because it actually, this one, right, is actually 2 decimal places further over there, right? So its significance is it's going to be an insignificant change. Okay. So then we can come back over here and put these numbers back in for X, right? Now our Ka is going to be equal to whatever we said X was, which was 2.294 times 10 to the negative 3, right? X times X is X squared, so we're going to square that number, divided by 0.148 minus X, which is 2.94, cheapers. 294 times 10 to the negative 3. Right? When we solve that number, Ka becomes equal to 3.61 times 10 to the negative 5. We follow units, that's going to be an M. Questions on that? Right? So we will find, the reason I showed this assumption here, right? Most of the time, this value we are going to assume to be 0, right? The reason I showed it today is, one, I want you to be aware that is that if X becomes very small, right, this autoionization of water becomes important. But the other is to show you this assumption, right? If the K values are small, right, that means that the amount that's going to dissociate to make this X is going to be also small, because a K value that's much less than 1 means that it's heavily reactant favored. Remember, we talked about when we compare K to 1, if it's greater than 1, we say that that is product favored. If it's less than 1, that's reactant favored. So those things that are reactant favored, the majority of it is going to exist in this protonated form, right? Which means that we can then, if we have initial concentration over or here, right, we could sometimes make an assumption for this that loss of X is going to be small, and then we can ignore it. Right? But when we do that, we have to write down this assumption and check it. Questions on that? So for these reactions, they're still equilibriums. We're still going to solve ice tables. Now the equilibrium expression that we're talking about is just going to be a Ka or a Kb, depending on whether the substance we have initially is an acid or a base. Right? So although the terms are going to change, the process at which we do these calculations is going to remain the same. Any questions?